And we're there. Good morning, everybody. For those who are in my time zone, actually, it is 9 o'clock. Um, we have with us today Evgeny Mandrikov, which is one of the creator of Jacoco, the almighty code coverage framework, and an awesome piece of software. Who's now working for Sonar Source? Has been working there for a while, and lives in Switzerland. Uh, so in the afternoon, in this case. Um, so I'm eager to see his presentation. So I'll leave it to him to get started. And good morning, Igivni.
Hello, hello everybody. So yes, my name is Evgeny Mandrikov, and I'm happy to present to you Java code coverage on the best friend bytecode today. We will have a bit of scandals, a little bit of investigations, and there will be some intrigues. So welcome. Um, Before we start, I should give you a disclaimer. Indeed, I work in a great company, Sonar Source, creators of Sonar, SonarCube. If you know those products, you might love them, you might hate them. I don't really care today. And whatever I'm going to tell you today has nothing to do with this company. Actually, this company can only dream that my employee owns my opinion. They don't. Whatever I'm going to present to you today is connected with my, let's say, night work on open source Jacoco tool or library. So let's move on. Java code coverage. That's what we're gonna talk today. And Jacoco, well, is acronym of Java code coverage. While developing this Jacoco library, nowadays we test quite a lot of GDK version. It's strange that the slide wasn't updated, but it's not 17, it's 21 and a half nowadays, including Y half, including early access builds. Why we test so many, we're going to see today. Sometimes out of this testing, indeed, we improve the tools, the Jacoco, but also sometimes we find bugs in GDK. This is quite interesting. This is quite fun. We're going to also see today which bugs we managed to find and why. And well, sometimes we implement new features. So, for example, some time ago, quite a long time ago, code coverage report produced by Jacoco version 081 for some code base with all the tests written looked like this. While looking at this report, you might wonder, well, probably there is not all tests. Probably there is something else to test. There is not 100% of coverage everywhere. But well, after implementing some features in Jacoco for exactly the same code base, for exactly the same set of tests, we got 100%. Why this happens, what we did is exactly what we're going to have a look today. Before we start, it's important to understand that Jacoco receives all the information from the class files, not from the source files that you write, but from the class files which are a result of a compilation of your source code into the bytecode. This is pretty neat property because, well, then we can simplify integration. We don't need to look at your sources. We don't need to modify your sources. We can just use Java agent, and on the fly, it will do all the measurements, all the transformations. Absence of source files is not a problem anymore for us. So we can take even some software for which you don't have any more source files, and well, we can measure code coverage on it, how many methods you executed, which methods were executed, etc. And well, quite some time ago, we saw that this is also a nice property because it would allow us to easily cover new language features. And indeed, new syntactic sugar is not a problem for us. Like, for example, text block appeared in GDK 15. They are only source level features. They do not change the bytecode. So on our side, support of text blocks was easy, do nothing. And well, some other syntactic sugar also won't be a problem for us. Like, for example, there is a JEP draft of concise method bodies. I expect that we don't need to do anything once they're implemented. And well, we had a dream that, well, bytecode is bytecode. If there is some languages which do compile into the bytecode, like, for example, Kotlin, Scala. So we thought, well, if we base it on the bytecode, all those languages compile into the bytecode, then we should just easily work for them. This is half truth, half not. We're going to see a little bit why this happens. So let's move on. And here is a real disclaimer. Sorry for this. There will be a little bit blood out of GVM. If you're not ready for this, well, maybe it's time to close or leave the session. I don't know. If you're ready, please stay. Well, we're going to see naked Java compiler. We're not going to use any IDE today. We are not going to use any fancy after completion or whatever, just a Java compiler. And well, we're going to talk a strong language today. We're going to talk mostly bytecode. So, and well, of course, I will try to do intense violence of your brain. We have, what, about 1 hour? Sorry for that. I hope you're ready. Let's do the check. Are you ready? Henry, are you ready? Well, I guess
it's harder to get the button than I thought. Okay, yes, I'm ready. Yes. I'm listening. Okay. I'm eager.
So, but now relax. Take your favorite cup of coffee. Mine is here from Java Day Odessa. Take a seat, relax, and enjoy. Let's start with something simple. We have a class. By chance, its name bless me. And there is nothing in this class. Like, there is no fields, no methods, nothing. It's an empty class. If you agree with me, I think it's empty. If you agree with me, please drop something into the live chat, like +1, yes, it's an empty class. And if you don't agree, also, please feel free to drop it something into the chat saying, no, come on, it's not empty. Let's check whether it is really empty. And doing so, we're gonna first compile this class. We're gonna use javac class name bless me. We compile this class, we receive a class file, and then after we receive the class file, that's also what we're going to be doing today and looking at is a bytecode. So we're going to be using Java P2, which is part of GDK distribution, standard tool. It exists on your machine if you install GDK, with two important arguments, -v and -p. -v verbose, -p show me privates. Together, those two arguments, I call them, please show me everything. That's what we will be doing today. We're going to be compiling the source code and looking into the bytecode using Java P2. So here we go. Java P -v -p, bless me. And we see the bytecode of this class. Here is when it was modified. Here is its checksum. It was compiled from the following source file. Here is its version. Major version 52 in the bytecode and minor version 0 actually means Java 8. So yes, I was using GDK 8 while compiling this class. Here is so-called constant pool. Constant pool is basically all the constants, all the strings, all the method references, all the names used later on in the bytecode. This is the first time and the last time you see the constant pool. On all the following slides, I will be removing constant pool because it's quite big. Basically, the rest of the class file just references the item from the constant pool. So let's have a look at the rest. And here is what we see. A holy place is actually never empty. In this, as we saw, empty class, there is actually a constructor. Indeed, Java language specification says, well, if you haven't defined a constructor for your class, one is going to be implicitly created for you. And well, constructor cannot be empty, so we see even some code in there. There is a super constructor invocation. You know, every object in Java inherits from Java-lang object, so we need to do the super constructor invocation. And well, we cannot just fall out of a method. We need to return from a method. So here is bytecode instruction return. What also we see a so-called line number table and source file name attribute. And this is only two things that connect the bytecode back to the source code. There is no column numbers, there is nothing else, only the line number and the source file name. In the line number table, what you could see is basically line 1 corresponds to the instruction at the following offset. In this particular example, it says that, well, our constructor declaration that is on line 1, starting from bytecode offset instruction 0, corresponds to the line number 1 in the source code, so to the class declaration, actually. Let's move on. Let's take a little bit harder example. So here is a Java code. What do we have here? We have an outer class. In this outer class, we have a private field, private int counter, and we have an inner class. And this inner class has a method that performs an increment of counter. So first question is it a valid Java code? What do you think? Can we write like this in Java?
Let's see if there are answers. I have mine.
What's yours?
Yes.
We don't need to guess today, so we are just gonna be compiling this. If it compiles, it's valid Java. Easy. And indeed, it compiles, it's valid Java. What we're gonna see in it if we decompile it from the bytecode? Again, my favorite Java, Java 8, major version 52. Here is an increment method. What we could see in it, well, couple of instructions. We do expect here to see an increment, right? This is the only thing that we did. But ouch, we don't see an increment. We see something strange. We see invocation of a method from an outer class with a pretty weird name, access $008. What's that? Well, let's have a look at the outer class. Here is this method. We never wrote this method, but it exists in the bytecode. It's package local. It's also static. And well, we could notice that it has an interesting flag, synthetic. We know the keyword in Java static. This is understandable, but we don't have a keyword synthetic. What's that? Well, remember, we will get back to this. Let's look what happens in this method. Here is our increment, which we expected in the original method. Why it got moved into the outer class? What's going on here? Well, the answer is pretty interesting. The answer is pretty funny. While in the Java source code, it's perfectly valid to access privates of outer classes. It compiles, it works. From the Java language perspective, that's fine. But from the Java virtual machine perspective, this is two different classes that lie side by side in the same package, but they're two different. And till quite some time, there was absolutely no connection between those two. And well, access to the privates of one class from the other class is not allowed. To overcome this discrepancy between Java language specification and Java virtual machine specification, compiler was doing this crazy trick. We need to generate a new method which is accessible, which is package local, and then we can access privates from this method. All that changed in Java 11. You might know that in Java 11 we got JEP 181, nest-based access control. So let's have a look at what changed. If we will take exactly the same source and compile it with Java version 11, major version in the bytecode 55, here is what we're going to see. There is no more additional method generated. We only see constructor and that's it. So we can significantly decrease the size of the bytecode. That's nice. And all that become possible because this relation between two classes was introduced. Here is a new attribute, nest members, that says, well, here is my member that is nested into my class. Here is my name outer dollar, and here is the name of the inner class inner. So please, JVM, provide to this inner class access to my privates. And here is an inner class. If now we look at it, we would see a new attribute nest host, which says, well, I'm belonging to this outer class, and here, And here is an increment, and there is no more magic anymore. There is just an increment of a private field. Let's move on. Let's take a little bit more complex example. Here we have two classes, class A and class B. Class A is a parent of a class B. And we have a two method, fun in the parent and fun in the child. And the only difference between those two methods is the return type is different. Well, the child one overrides the parent one and changes the return type. So the same question again. Is it valid Java? Is it allowed to do like this, or should I write in a class B that fun returns object? What do you think, Henry?
I'm afraid. I think it's not valid because there's no generic or overriding, but I think I'll be wrong, so I'll be sad.
Sorry, you're gonna be sad, but we don't need to guess again. It's super easy like this. We compile. If it compiles, it's valid. And well, it compiles. We can compile. We can then again decompile and look at what's going on here. So here is a class B. This time, to not take a risk of any changes, I took even not Java 11, but Java 18 that's been already there for quite a while. Major version 62 in the bytecode. Here is the method that we wrote. It has a signature, it returns a string, its name fun. Here it is, all fine, all good. We move on, and ouch. We see another method that we didn't write in the class B. This method returns object as unwanted, like here it is. It is there. And we can again see this strange word synthetic. It again appears. What's that? And well, what this method does, this method simply calls original fun method. It does nothing else than simply delegates the method that we wrote just before that we wrote in the source code. Sorry. Why this happens? Well, that's probably why Henri was puzzled, and that's why probably he wanted method fun to return an object. There is a places in our API where we expect class A to be passed. But those places as well would accept all the children of class A, so why not our class B? But all those places that expect class A, they do also expect to be able to call method fun, which returns object. So for those places, we do need to provide them class B with the fun that returns object. And here we go. Compiler again generates for us something to overcome these problems. Those places that expect class A, they would receive the method that they expect. While we still can, from the Java language perspective, during overriding, we can still change the return type. Let's move on. Increasing complexity of our examples. Switch by enum. Pretty old construction. It existed for a very long time. We're going to have enum with two values. Pretty simple, pretty stupid, false and true. And we're going to have a switch. Well, before switch expressions came, switch was requiring a default case. So here is case false, case true, default case. We compile this time. I'm not going to ask whether it compiles or not. It's very simple. It compiles. Let's decompile and let's look at what's going on. So here is our example. Here is a switch. It has three cases as we wrote, 1, 2, and default. But what happens just before switch? We did a switch by enum, but what we see in the bytecode is not at all a switch by enum, not even by the ordinal value of enum. Here is a switch by something strange. It goes to the class that we never wrote, $1. It takes a field from this class. Apparently, this field has an array type. And it goes at the index of ordinal of our enum. take something from there and perform switch on that construction. Why so? Let's go and explore this class that we never wrote. Again, this magical synthetic word, this class is synthetic, so we can probably guess that it was generated by the compiler. Here is indeed a field. It has array array type of ints, and there is a static initializer in this class. Let's have a look what's inside of this static initializer. Well, we take ordinal value of enum constant false, and we assign 1 to the into the position of array of ordinal of constant false. We do the same for true, but we assign 2. And that's a static initializer. You might wonder why this, why all this is needed. Let's get back quickly to the source. In this source, enum and the switch by enum happen at exactly the same class, at exactly the same place. But imagine that my enum is in one model or even in another application, and my switch in another model or in another application. So they actually compile it separately. And what could easily happen that I could, for example, decide to change order of enum constants. I could move false down, true above, false. But this change in one library shouldn't affect already compiled another library with a switch. The runtime behavior of this should not change. So if you will be using a switch by ordinal value, just flipping the constants true and false would change the runtime behavior. To protect from this, compiler again does a trick. That's why there is this assignments. They basically capture a map from the runtime ordinal value into the value that's been there during compilation, so that switch will work as originally compiled. So here is the trick, and let's move on. We've seen a lot of examples of synthetic attribute, and we've been wondering what this synthetic attribute is. We can find an answer on this in our Bible, in Java Virtual Machine Specification. Java Virtual Machine Specification says, basically, the class member that was not written in the source code, in the bytecode, must be marked with a synthetic attribute or have synthetic flag. Well, as in any language, there is, of course, exceptions from the rule. And Java Virtual Machine Specification gives us those exceptions. The only exceptions to this rule is instance initialization method representing a default constructor, class or interface initialization method, and implicitly declared members of enum and record classes. We've already seen some of them, like we've seen instance initialization method. It indeed was not synthetic. Nevertheless, it was generated. And, well, it also says that synthetic attribute was introduced in JDK 101 to support nested classes and interfaces. Exactly what we've seen, exactly this discrepancy between Java Virtual Machine Specification and Java language specification. That's the moment when they needed to denote synthetic constructions because they needed to generate them. What else? At this moment, you might wonder why there is exceptions to this rule, why we cannot mark everything what was generated as synthetic, why we cannot mark instance initialization method as synthetic if it was generated. Well, the answer is synthetic constructions, you cannot access them as a developer. You can never write a call that would compile into the call of a synthetic method. But instance initialization method should be available for you. You should be able to call the constructor. So it's not marked as synthetic. Well, let's move on. Why all this is important for bytecode analysis tool and in our particular case for code coverage tool Jacoco? Well, because we might come to the logical conclusion. We are not supposed to show to the users what they never wrote in their source code. We should be showing them code coverage on the source code that they wrote. So we should ignore synthetic methods. They exist in the bytecode. You are not looking at the bytecode, you are looking at the source code. And that's what we did quite some time ago. We ignored all the synthetic constructions. And let's see what's happening after that. Lambdas. Lambdas were introduced quite already some time ago. So here is a simple example. We have exec method. It accepts runnable. Here is a method fun. It basically uses lambda as an argument for the exec method. Please notice that on the line 9 there is a string literal joker. We print it on screen. Now let's compile, let's decompile, let's see what's inside. And here we go. Method exec, nothing special here. We receive runnable, we invoke method run on this runnable. Here is our method fun that we wrote that contained lambda. Where is joker? There is no string literal joker anymore. It just disappeared. Where is line number 9 where was joker? You could see the 9 here, but this is not a line number. This is offset. This is a bytecode offset, which says, well, line 11 corresponds to the bytecode instruction at offset 9, so basically return from the method. And line 8 corresponds to the bytecode instruction at offset 0, so beginning of the method. And between the beginning and the end, line 9 just disappeared. What's going on? If you scroll further, we could see another method. It again synthetic. We never wrote it. Its name is pretty interesting. Its name is lambda $fun $0. And if you look into its body, here is a joker. It got migrated into the new method. And here is a line number 9. So if you want to know more about this, you would need to go more into the mechanics of lambdas on JVM. We don't have today time for this, so we will move on with other examples. But this is basically internals of implementation of lambdas in JVM. This is internals behind the bytecode instruction invoke dynamic, introduced in Java 7 quite a long time ago to support lambdas. Again, why it is important for bytecode analysis tool, in particular for code coverage, because, well, we did this trick. We excluded all the synthetics that the compiler generated. And, well, after introduction of lambdas, it simply means that we excluded all the lambdas. You cannot get the coverage for the lambda body. So we had to fix this. And since this is implementation details, there is no at all any statement about this in Java language specification or in Java virtual machine specification. This is unspecified. How we could fix this? Well, Dragons here, we rely on implementation details. This may change in future. What we basically do, we say, well, yes, it is synthetic, but the name of this method starts from lambda $, so most likely this is lambda. We should not exclude it. And, well, as it is not specified, it's already got changed. In fact, in Scala, lambdas compile into the names with a different name. I believe it's unknown $ something. In Kotlin, they also compile differently. And we need to adapt our code coverage to all this, even though we just analyze the bytecode and all those languages compile into the bytecode. Let's move on. At this moment in time, everything what you've seen have been synthetic. So you might start to wonder, well, it's interesting, but not that much. Do you have something non-synthetic? Well, I don't, but there is plenty inside of Java. So let's have a look at something non-synthetic. Here is an empty enum. Now we know that it's actually not empty, even though I didn't declare it any constants. It shouldn't be an empty, right? We already know that there at least should be some constructor generated. If we compile it, if we look at it, we would see a little bit more than just a constructor. We would see field values. we would see method values, we would see method value of, and here is constructors that we've been expecting. And they are all not synthetic. Why they are all not synthetic? Well, we already know the answer. If they would be synthetic, we could never call them. But we do know that enums should provide a method value of to get an enum by its string representation. So here it is. It is generated. It unfortunately cannot be marked as synthetic. But well, this is quite important for code coverage tool, again, because we need to filter this all out because, well, users don't expect to test this. Why should we ask to test something if it is compiler generated? We should just trust compilers that compiler generates the right code. So here's all those methods. We don't want to write tests for them, so we need to exclude them from code coverage reports. So again, we are going and we are writing the filters for all these, which basically say, well, okay, it's not synthetic, but we know that this is enum, we know that this method value of, so we should exclude it. Well, we did this improvement in Jacoco version 0.8.0. We excluded value of, we excluded values, but we forgot to exclude the generated constructor. Well, turns out that some people like to have an empty enum. I don't know for what reasons, but in the empty enums, constructor is never executed, so we also need to exclude that one. Okay, we did this improvement as well. Let's move on with more interesting examples, coming to more modern versions than Java 8, Java 7. Here we go, Java 14. Java 14 gave us a pretty wonderful JEP 359, records. What is behind records? Let's have a look. Here is a simple record. It has just one component, x. We can compile it and we can have a look at what's inside. So there is a lot of bytecode in it. Here is a component. Indeed, we wrote it. It's there. Here is constructor. Well, we expect it to be there. Here is method to string. Well, as a Java language users, we do expect to string to be there, but we don't expect to test it. Again, we don't expect to write some tests to verify that compiler correctly generated to string. And it's not marked as synthetic because, again, we would have to then we wouldn't have then access to it. Here is a hash code which is generated. Here is equals. Here is accessor. Here is a getter for our component of a record. All of this needs to be excluded. All of this needs to be taken care of by bytecode analysis tools. Let's move on. Java 8 brought to us not only lambdas, but also other wonderful constructions. One of them is switch by string. So here it is. Here is a switch by two constants, a and bbb. And that's it. We compile it, we decompile it. Let's have a look. We had just one switch in our source code, right? But if you look at the bytecode, we're going to see two. Am I blind or not? Let's move back a little bit. There is only one switch, right? But in the bytecode, there is two. Why so? Let's have a look. Here is a hash code. So the first switch is not at all done by a string value. It's done by its hash code. It's a neat implementation detail of switch by string. Initially, bytecode had no way to do the switch by string. And rather than bringing this way into the bytecode instructions, it turns out that we can simply implement this feature by utilizing already existing features. For example, why not do a switch by hash code? With a high probability, just doing the switch by hash code, we would already choose the correct case because, well, different strings have different hash codes. So here is the switch. But, well, sometimes also strings do have the same hash code. And after doing this switch by hash code, we also need to do some string comparisons. So here we go, string equals. We need to verify that we picked the correct string. So here is comparison with BBB, and it happened that A has exactly the same hash code as BBB. So we need to do two comparisons to finally decide which case we choose, one or the other one. And then once we decided, okay, we can do final switch just by an int, which denotes a case. And here is the first case, and here is the second case. Again, why all this is important? Well, because if we just analyze the bytecode, we are going to see all those branches. We are going to see all those ifs. We are going to see two switches. And, well, user just wrote, two cases, but we are going to show him that, well, there is 9 branches. And some of those branches you never covered. You never wrote a test that studies one of those paths. Again, why it's important? Because, well, we need to filter all this out. We need to pretend that, well, don't worry, there is not 9 branches, there is just 3 branches in the source code, and, well, in the bytecode, all this is hidden. Let's move on. Java 12. Java 12 brought to us improvement on the switch. We got a switch expression, JEP 325. It's pretty neat. Now, if we use switch as an expression, we don't need to write the default case if we list all the possible outcomes of the switch. So, for example, if we list all the enum constants, we don't need to write default. This is pretty nice from the source code point of view. Let's have a look at what happens in the bytecode. If we use Java compiler from the version when this feature was just introduced, it was a preview feature, so we need enable preview. That's exactly what I'm doing. Here is our fun, where our switch was. We look at this switch. We was expecting to have just 2 cases because we don't need anymore to write default, but we have 3 cases. We still have 3 cases in the bytecode. Let's look at the default case. Well, here's the default case. The default case throws incompatible class change error. Why so? Well, because, again, what if somebody would have changed the enum constant and would add more constants into the enum? Our switch cannot just do nothing, or it should do something sane. And turns out that, well, sane behavior in this case is to throw an exception, denoting that, well, some incompatible change happened. So we need to generate the default. Let's move on. We got later on in Java 14 JEP 305. It brought even more interesting features to us, like, for example, pattern matching. Now we can write expressions like this. If something is an instance of some type, then, well, here is a variable that would have this type and would hold that value. So we don't need to write crazy casts. We can just write like this. If you compile this, if you decompile it, here is Java 14 when this feature was introduced. Again, it was at that time preview feature, so I use it enable preview flag. Enable preview flag appears in the bytecode as a magic minor version number, 65,535. Here is our example that contained this pattern matching construction. We are expecting to see here just one if, right? If something is an instance of something. Here is an if. Easy, right? But no, there is another if. But we wrote just one. Why? Why there is 2? Well, turns out that for developers of compiler to implement this feature, it was easier to say, well, it's just going to be a source-to-source transformation, and then we compile a new source. So the constructions that we've just seen, pattern matching instance of, and the bytecode produced out of it is just a compilation of this source. So we can introduce a temporary variable and do such a crazy casts inside of if condition. Well, this cast makes no sense. It always exists because, well, value is equal to itself. But this cast allows us to do the assignment. And that's how initially this feature was implemented. Exactly like this, source-to-source transformation and then compilation into the bytecode. That's why in the bytecode we can see the second condition. And this second condition makes no sense because it's always true. So again, it's a problem for bytecode analysis tool because bytecode analysis tool would see this condition and would believe that, well, there is multiple branches, but this is simply a dead code that can be removed. So, well, we provide such a feedback, one of the, let's say, bugs that we find, and it got accepted. So later on, when this feature goes out of preview, exactly the same source code compiles. So here we go, Java 16, major version 60. It compiles in just one condition. Let's move on. Java 17. Java 17 brought to us pattern matching in switch. Initially, at the time of Java 17, it looked slightly different from what we have nowadays, but let's look at this history. So what do we have here? Switch. We can have some cases. Every case can say, well, let's test a type. Also together with testing a type, we can test some conditions, etc., etc. Let's compile this. Let's decompile. Java 17, again, major version 61 in the bytecode with preview features enabled. Here is a method that we compiled. It's quite big. We can zoom in. Here is a switch. There is nothing special about it. We had 4 cases. We have 4 cases. Seems too much. All good. Here is condition of a first case. It's fine. Here is body of a first case. All good. If we don't have a match, we restart a switch. It's just little implementation detail. It seems logical, all good. So here is invoke dynamic construction, use it again, the same that was used for implementation of lambdas. It got reused here. There is nothing strange in this method. It looks normal. The only problem is if you look at the connection of this bytecode with the source code. If you look, well, looking at it like this doesn't give us much clue what went wrong with it. But when testing this new feature with bytecode analysis tool like Jacoco, we noticed that there is something strange here. We fire it up a debugger, and if you would be stepping at the time of implementation of this feature in a debugger through this switch, it will be showing you completely different lines, not the ones that you expect to be executed. That was a bug. This time we was even faster than the previous time. We didn't wait for this feature to be even merged into the master of GDK. We commented directly on the implementation of this feature and it got fixed. Pretty cool, pretty neat. But let's move on. Again, more complex and more complex examples. I hope you are still with us. I still hope you enjoy. Finally, we come to finally. Pretty old construction. Try finally. So what do we have here? We have a method fun. It contains try finally. We have another method called nop. It's called both from the body of a try and from the finally. Let's compile this. So let's decompile. Let's look at the method fun. Nothing suspicious here at the first glance, right? Let's move closer. Here is 3 invocations of a method nop, right? But there was only 2. Again, let's double check. Maybe there was 3 nops. Like, oops. Sorry, I could see 3 nops here. Like on the screen, there is nop, nop, and nop, right? No, the third one is not at all an invocation. The third one is actually method declaration. To help us distinguish, to help us investigate what's going on, let's add some marker. Let's add a parameter to the method and let's put the 2 constants and let those constants be different. Inside the try body, there will be constant try, and inside of finally body, there will be a constant finally. If we compile that, we're going to see following. What's the difference with the previous one? Now the difference is obvious. There is just one try body, but somehow there is 2 finally bodies. What's that? What goes on? Well, there is no try catch finally in the bytecode. In the bytecode, there is only exception table. So in the bytecode, you can do only try catch without finally. And this is implemented as so-called exception table. Exception table simply says, if from instruction number at offset this to instruction at offset z happen at exception of this type, then please go and continue execution at this target instruction, and that's it. So in this particular case, it says from instruction 0 to instruction 5, if exception of any type happened, then let's go to the instruction 13. How to implement finally with this? Well, in case of exception, we have execution of finally. Here it is. But we also know that finally should be executed both in case of exception and in case of when exception didn't happen. Finally should be always executed. So to overcome this difficulty that exception table cannot express this, we need to duplicate finally. One finally is on execution path normal one, and the other finally is on exceptional execution path. So here is, in case of exception, we use exception table. Here is exception handler, and in case where there was no exception, there is still finally. And well, again, this affects all the bytecode analysis tools. They see those duplications. It's a difficulty also for testing. You need to test both paths. So again, we need to implement some filter, more complex this time. This time filter should find the duplicates and merge them together to say that, well, don't worry, there is not that much execution paths. Also, for fun, here is a little home exercise. Because we get a little bit of duplication. No, okay, I will get back to this home exercise a little bit later. Let's move on. A bit of archaeology. This was not like this. There was no duplication quite some time ago. I don't know if you remember this time or not, but I do remember. If we go back at the times of Java 4, Java 1.4, major version 48, if we compile exactly the same source with Java version 1.4, here is what we are going to see. The difference is that there is no duplication. So at Java 1.4 time, it was possible to implement the same thing as today requires duplication. How was it possible? Well, here is exception handler. And here is wonderful set of instructions, GSR and thread. A long time ago, Java had a subroutines. Java had functions inside of a functions. This feature got deprecated, this feature got removed. GSR and thread instructions no more used nowadays. Why this happened? Well, we don't have much time to discuss this, but if you are curious, you can search for another talk of my friend Nikita about bytecode verification. All this was important for security, for the verification of the bytecode. So GSR and thread instructions disappeared. Let's move on. I hope now you're fully warmed and now you can really enjoy the hardest cases that I do have to show to you about bytecode. Try with resources. Try with resources was introduced in Java 7, again, quite some time ago. So what do we have here? We have a resource. It implements closable, so it has a method close. Here is try with resources. Here is a resource which is closable. Thanks to try with resources, we don't need to write all this logic about closing the resource. It will be automatically closed for us, right? So let's have a look at what happens in the bytecode. So here is a bytecode. I think it's pretty obvious for you all what is going on here. Sorry, I am kidding. I probably need to zoom a bit. Is it better like this? Probably still not. We need to zoom a bit more. Here, we start seeing something. Closable.close. There is 4 times call of a method close on our resource. Okay, we didn't write none of them. That's fine, because that's exactly promise of try with resources. Well, that closing will happen automatically, and here is closing. But why 4 times? Well, probably because, well, resource needs to be closed. So to be sure that resource is closed, we close it 4 times. Then we're sure that it's closed. Well, of course not. I am kidding. There is also some other magic. It's not just arbitrary for clauses. There is some null checks. And well, how to understand what happened? This time Java language specification gives us a clue, another Bible. The meaning of a basic try with resources statement is given by the following translation to a local variable declaration and try catch finally statement. So this time, even in Java language specification, the fact that try with resources is source to source transformation and then compilation was revealed. In this paragraph later on, they show this source code. So compilation of try with resources is equivalent to the compilation of the following source code. At this moment in time, you could logically ask, well, can you prove it that it's exactly the same thing? I hope I can. Let's give it a try. So let me increase a bit font size. What do we have here? I have fun1 Java. It's try with resources that we've just seen. I have fun2 Java. This is this beast from the Java language specification that we also just seen. Let me select, why not, my favorite Java, Java 8. I'm gonna compile fun1 from, what's the name of the class? Example. I'm gonna compile fun1 and I'm gonna decompile it. And I'm gonna save, let's actually, I'm gonna compile, I'm gonna decompile, and save result of compilation in 1.txt. For the fun2, I'm gonna do the same and save the result of compilation in 2.txt. Let's have a look at the diff between 1 and the 2. Something changed. Of course, something changed. Like last modification time changed because I had some delay between compilation of those two classes, of course. The source file name changed. One is fun1, fun2. Yes, fair enough. Line numbers are different. Fair enough. One has just more lines. But that's it. The rest of the bytecode logic is exactly the same. So indeed, we just proved that, oops, where is my up? We just proved that compilation of this source code is equivalent to compilation of try with resources. And if we closely look at this source code, it's easier than looking at this crazy bytecode. What we could see here, let's look. Here is a try catch. Here is a finally block. In case of exception, we need to close the resource. So here is a modification of finally. If there was an exception and we close the resource, there might be another exception. So we need to attach one exception to the other. Here it is. Here is the case if exception didn't happen, we anyway need to close the resource. And this time we don't need to attach one exception to the other. So we let it just bubble up. And well, here is another condition. We need to check if resource null or not. Because if on a null resource we call close, we are going to get null pointer exception. But in this particular case, this null check is absolutely useless because we just instantiated the resource with a call of a constructor, so we know that it's not null. This is a dead code. Here is another dead code. In a cage body, we do know that exception happened, so we don't need to check whether exception happened. But you already know that finally is inlined on all the exits from that try catch, so including the try body, the cage body, and so on, so on. Well, again, different bytecode analysis tools, including Jacoco, who else was reporting this. I believe Findbugs at that time or Handbugs was reporting that there is a dead code in compilation with try with resources, and this got improved. Initial version had 4 if checks, if null checks. It got improved down to 2. Then Later on in GDK 11, it got improved further. GDK 11 still was capable of compiling down to the bytecode of version Java 8. There was 2 null checks, and now there is 0. Wonderful reduction in the bytecode size. So here is what was happening on the Java compiler side, but on our tool side, we cannot just pretend that, well, improvement happened and we will wait for this improvement to happen. Of course, we need to adapt to all of these changes. We need to write the filters, and those filters should look at the bytecode and see, oh, which version it is. If it's that version, we need to ignore those constructions. If it's that version, we need to ignore some other constructions. We did all this, we did all those improvements, and here we got, again, 100% coverage. What's funny there is we just proved that compilation of try with resources at some moment have been exactly equivalent to the compilation of some source code. The bytecode was exactly the same, and our tool doesn't look at the source code. Our tool just looks at the bytecode. So from the point of view of Jacoco, there is absolutely no difference between one source code and the other. You might wonder, how do we distinguish try with resources from its equivalent that is not try with resources? Well, not so secret, but telling you like a secret, we don't. We are not capable of distinguishing these two situations. We just say, okay, if it looks like try with resources in the bytecode, it should be the try with resources. Hopefully nobody in the world writes try with resources without writing try with resources, so we are safe. And even if somebody would be able to write try with resources without try with resources, then this try with resources is correct. We are not going to be showing coverage on it, but then it was correctly written as if compiler would write it. So here we come to the conclusion and to the end of this talk. Source code is not the bytecode. Be aware. So whatever you write in the source code, not at all what is going to be executed. There is a dragons. Be careful. It's going to be compiled by the compiler into the bytecode, and bytecode might have something what you never expected, like accessor methods that we've seen just at the beginning. It's additional overheads. They might affect your performance of your application. There's various other interesting things. But also be careful. Well, even the bytecode is not what is going to be executed. You know, there is a just-in-time compiler, which is going to take result of compilation, which is bytecode, and then compile it further into the native code. Even this is not at the end of the process. The native code is then going to be executed by the processor, and processor can do other crazy things like branch prediction, etc., etc. So be careful. Not everything what you write in the source code executed as it is written. There might be bugs, there might be dragons. Bytecode, another conclusion is that, well, bytecode-based tools sometimes have to guess. They don't have any choice other than guessing, as we've seen with try with resources. So please, please, please bear with us. Developers have to somehow live with this. We developers of such bytecode analysis tools should find a ways to filter, to present results better. And you developers, users of those tools, should be aware that, well, what you're looking at is not exactly the source code, because this tool performs analysis of something else. So now you're aware. If anytime later you step on some interesting case and you're wondering why your favorite coverage tool shows you something strange, now you know what to do. Now you know that you just need to compile, decompile, and look at the bytecode. And that's it. Thank you for your attention and hope you enjoyed.
Thank you very much. That was super fun. I'll go to the questions and comments. There was one nice comment by Vincent Vauban, who's saying that bytecode. You made bytecode actually readable, so people now realize that it's not that terrible to read, which is cool. Uh,
Yes, that's awesome.
and then Marianne Varga is saying was talking about Lombok, which is a bit like Kotlin. So I don't know if you handle Lombok specifically.
Um, we do handle Lombok. There was, I think it was a contribution, external contribution, if I'm not mistaken. We don't handle all the Lombok. We handle methods generated by Lombok. So I don't know how much, maybe 50% of Lombok cases we do handle. We don't handle constructions like when something is declared as not nullable and Lombok injects null checks. This we don't do. Um, Personally, I'm not a big fan of Lombok, so that's why
You
it
have a
never been
supporter.
a priority
Not
for me.
use it. Do not use it.
Uh, well, maybe we will do it, maybe not. Nowadays there is some other alternatives to Lombok. Like there is, sorry, it's, I don't know if it's Java conference or just a GVM conference, but there is Kotlin with a wonderful type system
Mhm.
with nullable and not nullable types. And there is rumors that we might get also enhancement in the Java type system with
Yeah,
nullable and
with
not
value
nullable
types.
types.
And
So
yes,
maybe time when we don't need Lombok is just around the corner.
I hope, I hope, I hope. And yeah, and I could even argue that Lombok is generating code. You can assume it's good, but you cannot fully assume it's good. So testing it, it might not be an actual bad thing. There was a similar question with Mapstruct, and actually it means that like all libraries that are generating code, of course, it's generated, but Jacoco can know about all of them. So yeah, it will show.
Um, we've been trying to cover case by case, like we covered generated code in case of Groovy, then Lombok, and then Apache, I don't remember, Apache Avro maybe, they came and said,
Mm,
oh, we also would like our code to be filtered. Instead of handling case by case, we said, okay, fine. If any of those frameworks places an annotation on a method whose name contains generated, we would assume that this is a generated code. So
mm.
if there is a libraries like Mapstruct out there that still generate some code and they don't place generated annotation on the generated methods, classes, etc., then please just go to them and say, well, be nice, place the generated annotation so that bytecode analysis tool can distinguish generated code from a human read.
That's a great trick, actually. Cool. Thank you. Another one by Marianne. It's about when you talk about finally, yeah, it will duplicate the bytecode since they put the finally part twice. So yeah, if you want to reduce
That's
your
that's
class.
a real that's a really great question, and I wanted to put a little home exercise for attendees. So, indeed, there is a duplication. You can experiment with this duplication after the long day at the evening, just for fun. You could try nesting try finally into the finally, and you could try see at which moment it will stop compiling. This moment is not that far because indeed it's exponential growth. Every time you nest, it doubles. And there is GVM limits on the bytecode size. You would reach pretty quickly this limit. So the exercise is to see how many nested try-finalies you could have in Java.
That's fun. Hmm. So actually, if you want to do something really small, you might need to extract methods from your finally to shorten them, which is quite cool to know. Uh, and the final word. I agree.
Well, um, I cannot disagree. I cannot disagree. It was more of a joke. So, well, let me tell you the truth. Java 8 is not my favorite Java version. It was for a quite long time. It was a fresh air after quite some years of no evolution in Java, and then Java 8 came. It was wonderful. A lot of people stayed on it for too long. Some people still stay on Java 8 for too long. Yes, they should move forward with what is LTS today? Java 21.
Yeah.
Just go to Java 21
Mm,
if you can.
yeah.
And here is another sad truth. My favorite version is Java 5.
Ah, is
Well,
it?
that's also half joke, half truth. Jacoco is still compatible with Java 5.
Oh,
Unfortunately, we do know there is still some users out there that use us and that have this
oh
ancient
dear.
version in the production.
Poor people.
Yes, poor people. We are extremely careful on non-breaking the user experience, so we never took it seriously. We never said, let's break the compatibility with Java 5. I start feeling that this breaking change is around corner. We need to finally break compatibility with Java 5. Unfortunately, another sad truth is as much as I would love to go to Java 21, the reality there is a lot of people still on Java 8. So
Yes.
most likely we will break compatibility with Java 5, but our next target will be not Java 21, but Java 8.
Mm-mm. I think I think it went down like 30% of what I see or something like this, but it's still pretty frequent, and it's still
In
really hard to go 8 to 11. That's the
yes,
problem. After it's easy, and anybody can do it.
yes, it goes down, but it goes down slowly.
Yeah. I think it's a bit. I don't. I would like to compare with Java 5 because Java 5 was hard to go to. So I wonder. I don't remember how many times it took for people at that time. Uh,
Well, I'm not
uh,
gonna name the companies. I'm not gonna give any insight, but quite recently, one of my friends worked on helping some big customer to migrate Java 5 code base to Java 6.
hard, but it's really Java 5 code base, or they use libraries that are old and so compiled Java 5 or something like that, or
Well,
it's really their source.
their runtime is Java 5.
Oh wow, okay.
So yes, they do use libraries that Java 5 compiled. Poor people, but well, they do exist, unfortunately.
Okay, yeah, there's people amazed by that in the comments. Um, and one question on my side, when you do records, because for records, methods are generated, so you have like the getter and toString and things. But if I override them, I do my own code, and it will look pretty much the same, apart from the bootstrapping in there. So are you guessing if it's the original or my override, or you just knew your stuff and that's it?
Um, Let me remember. So in case of toString and hash code, we are not guessing. You cannot write exactly the same bytecode because there is invoke dynamic.
Yeah.
And
Mhm. So you look at the content of the method and say,
yes,
okay, there's a bootstrap call here, and okay, so that's
yes,
the
but
original.
for getter, unfortunately, I think indeed we cannot distinguish getter from the
Yeah,
handwritten one.
because the getter, they will be just like a load return, I think, the original, because it's
Lot and
really
return.
plain.
Yes.
So, and if I override, the only thing you could guess, like, there's more than that.
Yeah, but again, if it's exactly the same as
Yeah, of
compiler
course.
generated, it's okay. But indeed, this gives us a hard time every time we decide to filter out something. We need to think whether user could write some source code that will look similar to what we filter out and not exactly what compiler generates.
Mm.
It's easier in Java, I have to say, and it's harder in other languages.
Mm. You
Like
mean like
in
Kotlin, Scala, these
in
things?
Kotlin, it's much easier to write two different source codes that would compile into exactly the same bytecode. And
Okay.
where the difference is really significant and would be misleading to assume that those two are identical.
Okay, interesting. We are way over time, so I'll let people go to the already started other sessions. But but that was all for all the questions. Thank you very much. That was great. I had a lot of fun.
Thank you. Enjoy the rest of the day, everybody.
Thanks. See you. Here we